Hello students, so today we will start with the urban ecosystem and water, and we will cover under this the water cycle, that's the natural water cycle, key processes in the natural water cycle, modified water cycle, key urban water challenges, integrated urban water management, policies and paradigm shift for future. Water cycle, as we know, the hydrologic cycle it is, and it is having a continuous circulation of water within the earth and atmosphere system with no beginning or no end. The cycle connects the hydrosphere, atmosphere, lithosphere and biosphere. So if we have to understand this natural water cycle, let us understand first the key processes involved. In this particular image also you will find the processes well documented like evaporation, condensation, precipitation, interception, infiltration, percolation, transpiration, runoff and storage. And we will come back and discuss them one by one. Major feature, there will be a pool and there will be fluxes. Pool means reservoirs where water is stored like oceans, glaciers, aquifers. And the fluxes, that's the processes that move water between pools. Just now we discussed those processes, evaporation, precipitation. There is also advection, horizontal movement through the cloud. So natural water cycle, if we start discussing about the fluxes, let us first discuss the atmosphere and surface exchange. That is earth system and the atmosphere. Evaporation, the primary flux returning water to the atmosphere. How? Through vapor. Evaporation, liquid to gas phase change driven by the solar energy. Oceans contribute 90% of atmospheric pressure almost. Next process we'll be discussing is the sublimation, direct conversion from solid ice or snow to water vapor. So there is no liquid phase. Next one is the transpiration, evaporation from plant leaves, even the soil also transpire. Accounts to 99% water absorbed by the roots. Condensation, water vapor cools to its dew point, changing back to liquid and forming the clouds. This process releases latent heat, a major driver of the atmospheric circulation. We will discuss the latent heat again. Now we will be discussing the fluxes which is happening on the earth: precipitation, infiltration, percolation and runoff. So in the precipitation we get water droplets or ice crystals that fall as rain, snow, sleet or hail. This is the primary delivery of fresh water to continents. What is infiltration? Now once that rainfall has happened, how that particular water is getting soaked into the soil from the surface, that process is infiltration. But infiltration and percolation, they are two different processes. Through the percolation, the downward movement of that infiltrated water continues through the soil and rock, and they replenish the groundwater aquifers. And the last part we'll be discussing, that's the runoff. It is getting generated when precipitation exceeds the soil's capacity to infiltrate. That excess water flows over the land into streams and rivers. So let us see the global water distribution pattern. Ocean is having almost 97% of the earth's water, but it is saline. Only 3% is fresh water, and most of them are locked in the glaciers, almost 70%, or else the rest is groundwater. Atmosphere is having a very small share, 0.001%, but very important because they act as a superhighway for water transportation. Whatever we discuss, that precipitation or evaporation, you need atmosphere to have all these. Now let us also have a good attention to the residence time. The average time a water molecule spends in a reservoir, that's a pool, that is atmosphere, around 10 days. In the rivers, 2 to 6 months. But in the deep ocean, it can be 3000 years or so. So you can easily understand this residence time is also equally important for the scientist, hydrologist to understand this movement. Now let us understand how this process is working, which is the engine for this water cycle, if water cycle can be compared with a car. Water cycle is an energy driven system. Primary energy who provides solar energy, and the latent heat of vaporization that comes from the solar energy, and it is required for evaporation and evapotranspiration both. This energy is stored in water molecules both as liquid and the vapor phase. Latent heat release: when vapor condenses, this stored energy is released, warming the atmosphere or water pools, and they drive the weather patterns and the storms. So latent heat is a wonderful mechanism through which water cycle is actually getting the process on. Another very important factor is the gravity, the force that pulls water back to the surface as precipitation and drives its flow in runoff, stream flow, and groundwater movement. We would like to now see the modified water cycle. If urbanization is happening, if the development is happening, how they are impacting this hydrology. So, urbanization, we can safely say, is a drastic and permanent modification bringing to the landscape that is fundamentally altering the hydrological cycle. What are the key physical changes we can find? Creation of impervious surfaces like rooftops, roads, and parking lots. They are preventing the infiltration. Very basic process for the cycle. Removal of natural vegetation reduces interception and evapotranspiration. Construction of artificial drainage, how it is impacting. Storms, rivers, and the channels, they accelerate because it's a smoother surface. They accelerate the runoff, bypassing natural flow paths. So, giving the enough chance to the soil to get it soaked, that is now lessened. Urban heat island effect, that can also alter the local precipitation patterns. Now let us see, it's a good graph. We will start understanding that how hydrologists, they monitor, they track this modified water cycle. You can see in this particular graph, x-axis is discussing about the time, y-axis is talking about the river discharge. So the particular concept which has been presented in this particular graph is, there is a storm and then this is getting plotted. So it is monitored that how the stream is getting the discharge over time after a rainfall event. You can see there are several rainfall events here. These bars are actually representing that rainfall. Immediately there will not be the discharge, there is a flow process which we discussed. So river base flow will continue like this, and if there is no urbanization, then river base flow will continue like this. If in the suburban areas we try to look at that type of development has happened, then we will see even if the peak is here, after a gap of the time, we can see that peak in the stream. So there is a lag time, and that is not hugely dense urbanization. But when the urbanization will happen, we will find that this is actually having a peak here very quickly, very short time lag and very high peak. So both the things are very important that the within a very short time and a very high runoff flow will come to the river. So, from this we can easily learn that natural watershed hydrograph always having a gentle rise with a low peak flow, which we saw with this blue one, long time lag between the storm and the peak flow. Whereas we can see the same thing also is true to a certain extent with the peri-urban areas, but urbanized watershed hydrograph will have a very flashy type of behavior. Much more shorter lag time. We could see it's only this much. And significantly higher peak discharge, that also we saw here. The discharge is here, whereas this discharge was here. And greater total runoff volume, that is equally, which comes under this particular graph area, that is the runoff volume. So that is quite high in comparison to the others. So this altered hydrograph is a direct cause of increased urban flooding. So we have to remember that what happens, what is the hydrological processes which is getting modified, and then only probably we can actually think about urban flooding and its mitigation adaptation processes appropriately. So let's see the role of impervious surfaces. Increased impervious cover is the single most important factor altering the urban water balance. It causes a dramatic shift from the infiltration and evapotranspiration to surface runoff, because there is no chance of infiltration now, or less chance, I will say. In natural conditions, about 25% of rainfall seeps into aquifers and only 10% runs off. Whereas in the urbanized areas, more than 50% becomes the runoff, while deep infiltration drops sharply. This excess runoff demands more drainage infrastructure, often converting natural waterways into concrete channels. As infiltration declines, groundwater levels fall, affecting wetlands, vegetation, and water supply, even for the city. Now, let us have a good look at this particular slide. You can see in the left hand side, it's a natural ground cover, that's the condition. Whereas on the rightmost, we can see it's a fully grown city, almost 75 to 100% impervious surface. So, from the natural, gradually it is losing its perviousness. It's a 10 to 20% impervious, it's a 35 to 50% impervious, and then 75. And in each cases, we can quickly have a glance at the rate of evapotranspiration changes. From 40% it is coming to 30%. What is happening to the deep infiltration? 25% to 5%. What a tremendous, what a tremendous change we can find here. And the runoff, the most important thing which we can measure easily, that from 10% to 55%. So you can easily imagine the power of urbanization to modify this water cycle. So it is also leading to the diminished groundwater recharge and increased flood volumes. Hydrological consequences of urbanization can be discussed further. Increased volume and velocity of urban runoff lead to the urban stream syndrome. What it is? Increased flooding, which we discussed already. Channel erosion. High velocity runoff scours the stream beds and erodes the banks. So it is widening and simplifying the channel, and it is also making the management more difficult. Habitat degradation. Erosion leads to sedimentation, which smothers habitat for the aquatic insects and the fish eggs. And this is resulting in severe degradation of the aquatic ecosystem. Biodiversity is lost. Also, ecosystem service from the aquatic ecosystem is also getting lessened. Degradation often begins when watershed imperviousness exceeds a critical threshold of 10% or so. So that is a good check. Now we will be discussing the water quality degradation. Impervious surfaces collect pollutants which are washed off during storms in a concentrated first flush. What are these non-point source pollutants? So it's not a point one which you can fix easily. It's happening everywhere, like sediment from the construction sites, heavy metals, hydrocarbons, nutrients from fertilizers, pathogens from pet waste and the sewer leaks, litter and debris which is getting joined into the stream. So they are really becoming nuisance for the stream. Thermal pollution, another very important one to control the habitat biodiversity. Runoff heated by these hot asphalt raises this particular pollution because our surface has changed and this is now becoming hotter. So, whenever the runoff will come after the rainfall, that is also having the higher temperature. So, stream temperature is rising, which is actually impacting the dissolved oxygen status as well as the stress it is creating on the aquatic life. The engineered urban water cycle, let us understand that how we are trying to manage it. Urbanization introduces a separate engineered cycle to manage water for human needs because we need it for a continuous supply as and when it is required. Our demands are also different than the natural system. Sometimes it may be for the residential, sometimes it may be for the industrial purpose. So, depending on those purposes, we need water. So, what is the process? Is not a closed pipe to pipe system, but it is interacting with the natural cycle because it has to get the source also. So, 8 major steps which we can discuss, that's the source. Source are natural, rivers, lakes, aquifers, but then that water is getting treated. Then it is going to be distributed. For the distribution, we are having the storage and the distribution pipes. Then the usage is happening. Wastewater, once the water has been used, we are having the wastewater. That water needs to be collected and treated so that the treated water only comes as a discharge to the environment, or we can in today's time discussing ferociously the recycling of this water. So, when the hydrology group of the city management system is trying to manage this water supply system, they have to always depend on this water balance equation. This relationship is actually discussing what are the inputs and what are the outputs. Once we understand them clearly, then we do understand the storage part where the problem lies. Like in the formula only you can see the sources or inputs are precipitation or imported water. That is also the case for an urban areas. We import from some other sources. Then the groundwater inflow. So these are making the inflow side. Outflow side, let us see evapotranspiration, it is the loss. Then the runoff, which is going without giving the water chance to reside. Then there is the wastewater discharge. And whatever is rest between these two input and output, that is the storage or change in storage, I will say. That can be in the reservoirs, in the soil moisture, or in the atmospheric moisture as well as the aquifers. And to do this, the essential data requirement is very important to remember. That is rainfall intensity and duration, runoff coefficient, runoff coefficients for various surfaces, detailed land cover information like impervious or pervious, evapotranspiration rates, groundwater levels and the soil characteristics. These are some basic data required. So, let us just see the urbanization footprint. In this particular image, we can find whatever we have discussed that has actually been talked here. that reduced infiltration due to the impervious surfaces like roads and roofs. Increased surface runoff leading to higher flood risk, which we have discussed. Engineered systems like drains, sewers, they redirect the water flows. And piped water supply and the wastewater create the artificial flows, which is important for the urbanized system, which is controlled. And when we look at the natural system, we can easily understand that natural water cycle has its own strength: high infiltration, low surface runoff, balanced evapotranspiration. So, which is helping all the spheres. Whereas in the urban water cycle process, the way we manage, that is only targeting the anthroposphere. So, when we look at this modified water cycle and try to understand that what is happening there, we could really identify the core problem, which is urbanization is actually decoupling the water from the land and treating rain as a waste product, which you need to remove as early as possible, rather than how nature handles it. Nature handles it as a resource which nature manages quite efficiently. So, when we try to look at this two different systems, natural versus the urban, we can easily see the differences, the dominant pathways like infiltration into the soil and evapotranspiration by plants, whereas in the case of urban water, it's the surface runoff. In the flow regime also there are changes. It used to be slow, diffused flow with water being stored in the soil, and then it will be released gradually. In case of urban, it's a very fast, concentrated flow designed for rapid water removal. For that only we design the drainage. What's happened to the water quality? Soil and vegetation will act as a living filter, and it's a ingrained system. Whereas our runoffs in the urban areas are getting collected and it is full of pollutants from the impervious surfaces. So, definitely the water quality is degraded, and also we cannot forget that raised temperature of that water. In the groundwater interaction, we can see the areas of groundwater recharge is always there in the nature's plan, but in the urban water system we find that recharge potential areas are gradually getting grabbed. So that's a big problem for the urban areas. Not only it is having the flooding, but it is also having the problem of water scarcity. So these are the summation of urban water challenges. Urbanization drastically alters natural hydrology, impacting runoff patterns and groundwater recharge. So we could find that water related issues like urban flooding, water scarcity are very common. Water pollution also we discussed, contamination as well as the temperature. Aging infrastructure, that is another problem for the cities, and it's very expensive to either retrofit them or realign them. Groundwater over extraction, that also leads to the not only scarcity of groundwater supply, also to the land subsidence. In addition to that, we are also having another great threat. It's a growing one, that's the climate change. And this is altering the precipitation patterns. Even in today's time, the settlements or towns in the desert areas, they are also now recording the problem of the flooding. More intense rainfall events can lead to flash floods, while prolonged droughts can cause the water scarcity. So, the same city in today's time during the summer is facing the water scarcity, as well as during the monsoon season, it is getting the problem of urban flooding. Increased evaporation. Higher temperature reduce the water availability from the surfaces and reservoirs. There are two parts into it. One part is higher temperatures, so increased transpiration or evaporation. But at the same time, the sources are also getting reduced. So chances of having the evaporation is also less. Sea level rise, impact on water quality. All these things are very important challenges posed by the climate change threat. In the mega cities, we can find that in these densely populated areas, water challenges are amplified. And that is making sure that we go for adaptation and other type of intervention where innovative ideas are being integrated. So it's a much more stronger policy and management driven initiatives. I will quickly bring certain examples from the world who have faced these problems, and the problems are different depending on their location, depending on their own context. Like Singapore is a highly developed country, limited freshwater resources, urban density is high, and the extreme rainfalls events are happening. So they have tried to understand how to really resolve it. They have tried to bring back that larger areas for groundwater recharge like parks and all this. They have also tried to bring back the wastewater not only for non-potable use but also for potable use. So new water they are actually now is a wonderful example for recycling. That's the type of quality they are bringing in the recycled water. Catchment management they are doing much more efficiently than previously. Copenhagen has the problem of this sea level rise is next to the sea. So the climate change is actually making sure that they can look at their sewer system because their combined sewer system is overflowing. Urban flooding is happening. Urban water quality at the harbor side is also degraded. So accordingly, they have tried to bring solutions and they are actually applying them. That is the beauty. In the Mexico City also we can see the over extraction of the groundwater, land subsidence is happening, water loss from the leakage, non-revenue water that is increasing, drought conditions are there. So you can look at the solution side. Similarly, Cape Town became a, I will say rather not so, in a positive way, but it becomes famous for their zero water. They were almost approaching to zero water scenario. So severe drought, their reservoir levels came down. They had a dependency on the very limited reservoirs. Population growth was another layer of pressures. So now they have come back heavily on the water conservation thing. Their infrastructure has upgraded. They have a very good management system in place and community is also actually participating. Similarly, we can look at the Tokyo which is having a problem of not only earthquake but also drought. Regular droughts they are facing and for that they have also understood as their location is also next to the sea how to manage this water will be a very important aspect for their position in the global scenario. So they have brought many different water efficiency measures including the harvesting, forest preservation, having the very strong engineered interventions like large tank. So those are the things they have already incorporated. We can look at the Melbourne also, urban water pollution, urban stormwater pollution, traditional drainage system overload, waterway contamination. These are the problems Melbourne faced. So what they have done, they have improved their wetland management, rain gardens, stormwater harvesting. These are all nature-based solutions which they have actually been able to bring into the system. And now their stormwater harvesting is probably one of the highest in the world. Green infrastructure integration and they are now having a vision of city as catchment. Now we will be discussing integrated urban water management. It's a solution where a holistic framework is being looked at, and it is actually having the entire urban cycle as a single interconnected system. That's the philosophy. Core tenets of this integrated management is view all water as a resource, not as waste, whether it is a stormwater or wastewater. Next thing is the match water quality to end use, fit for purpose. If I am using it for my industry or if I am using for my residential purpose, the water quality will differ. Integrate green as well as the grey infrastructure. So both engineered and the natural infrastructure shall get a place to be there in a symbiotic fashion. There are a lot of good applications we have seen. Water sensitive urban design and low impact development are some of the good example of this integrated water management. So in this particular management, as I discussed earlier, it's a holistic approach that is required. You have to consider drinking water, wastewater, stormwater, groundwater as an interconnected system. And this emphasizes on conservation, reuse, efficiency and risk reduction. This also includes demand side strategies, not only supply side strategies. One of the good examples which we will be discussing, that is the municipal water system. In that we will first discuss the water treatment and then we will be discussing how to bring back that wastewater which is coming out of the system into the use. When we need the water treatment before supplying it. So to convert the raw water into say potable drinking water, that means converting the sourced water into a safe water. In this, we have seen the application of this integrated management. This is a multi-stage process, like first coagulation and flocculation is required. Using the chemicals like alums are added to clump the fine particles together so that the flock can be formed. Then these flocks, when they will come together and create a heavier flock, then they will settle. So that's the sedimentation. So gravity will help that. But for that, the basin, the pool has to have the very low flow, quiet basin. Next step is the filtration. Water is passed through the filters, sand, gravel, carbon or advanced membranes to remove the smaller particles. And the fourth stage is the disinfection. So after this disinfection only, we can send this water for the distribution. And another example we will pick from the end of that cycle, where we can discuss the wastewater treatment, where our objective will be to remove the pollutants from the wastewater and the sewage. Primarily, I will be discussing the sewage water treatment, and wastewater treatment also will be very similar and you can study that of your own. So the first stage here will be preliminary and primary treatment, physical one. We have to have the screens and the grid chambers which will remove the large objectives and heavy solids. Primary clarifiers allow organic solids to settle as sludge. Then the secondary treatment, that's the biological one, the activated sludge process, that will use the microbes, the microorganisms and oxygen to consume dissolved organic pollutants. And again the last stage is the disinfection. Treated effluent is disinfected before discharge. But as I told you, the example of Singapore, they are not only utilizing the treated wastewater discharge, but they are also using the sewage water. After treating, they are bringing it back for recycling and use. Let us see the scope for integrated urban water management in the wastewater treatment and the resource recovery. Today's time, the paradigm has shifted from treatment and disposal to the resource recovery. advanced nutrient removal, biological process to remove nitrogen and phosphorus to prevent the eutrophication. Otherwise, this particular ecosystem will get the challenge of eutrophication. Membrane bioreactors combine biological treatments with the membrane filtration to produce high quality effluent suitable for reuse. Energy recovery, anaerobic digestion and sludge produces biogas which can be used to generate electricity and heat for the plant, and it is being utilized. It's not theory anymore. Nutrient recovery, phosphorus can be recovered and processed into fertilizers. So likewise we can see the wastewater can be treated, and from that we can have so many different type of resources recovered and also bringing back into the cycle. So once this wastewater is being treated, let us see how we can reuse and recycle. The practice of capturing used water, treating it to an appropriate standard and using it for a beneficial purpose is now very common. What type of reuse we see? Non-potable reuse for applications like irrigation, industrial cooling, toilet flushing, car washing, etc. Potable reuse, treating water to meet or exceed drinking water standards. Indirect potable reuse, purified water is placed in an environmental buffer like aquifer, reservoir before being retreated. Or else directly purified water can be piped or bottled. Now let us see the smart technologies for these water futures. Advanced tools and digital innovation empower cities to manage water more intelligently. Key examples include urban water balance models. Now we are having computational power, so we can simulate and predict how the water is going to move, and we can inform infrastructure planning under the different scenarios. Smart water networks, we use the sensors and IoT devices for real-time monitoring for water quality, pressure and leakage. GIS and digital tools, in today's time they are becoming just next to normal to be utilized for this water management. They can map the water infrastructure, analyze the land cover, model the hydrological features, and thus they help us. Now let us see some of the smart technologies. We can see the water efficient appliances, like in the toilets we are having the dual flushes, our taps are now having aerated water flow. Smart metering, which is very important to measure the efficiency of the system, and it can also help us in detecting the leak. Public awareness campaigns. This is something is very important to understand that water management systems, especially in the urban areas, needs to have public's participation, community participation. Then only that water will be properly managed. Otherwise, the resources, the sources are actually finite. Until and unless public participates, we will not be able to utilize that finite resource. And tariff structures that promote conservation is a good example of smart governance. So, we have seen whenever there is some tariff structure, people know how to utilize that resource carefully. So, let us now conclude this discussion on the urban water. Two parts we will be discussing, certain policies we will be discussing first, that is decentralization, shifts towards the smaller site scale systems, resource recovery which we discussed, smart water grids, use of sensors, IoT, AI for real time monitoring and optimized control of entire water network. Climate resilience in today's time becoming next to compulsory. Diversifying water portfolios with conservation, reuse and non-conventional sources. Another things we have to also discuss before concluding this discussion towards the sustainability, that is we have to have a changed paradigms. Like integration, it has to have a integrated fashion. We were discussing integrated urban water management, adaptation, flexible strategies for changing climate conditions, innovation, and cooperation, engaging all stakeholders to achieve these sustainable outcomes. So today we have discussed water cycle, key processes in the natural water cycle. Then we have discussed the modified water cycle, key urban water challenges. Then we came to the solution side. We discussed a lot on the integrated urban water management. Policies and paradigm shift for future will actually take us forward. With this, you can have a look at the references and thank you.